Here we're going to look at another number patterns and sequences problem. So, the diagram shows a sequence of triangle patterns. All small triangles are congruent or identical, which means every single one of these have exactly the same dimensions. Let T of n be the number of small triangles in pattern n. So for example, T of 1 will be 1 since there's only one triangle. And let P of n be the perimeter of the figure in pattern n. And we can suppose that P of 1 is 7, or in other words, the perimeter of the figure right here is 7. That will be handy later. So first we need to complete the following table. To complete the table for T of n is just pretty simple. Notice that for T of 1 we have just one triangle, T of 2 we have 4 triangles, T of 3 we have 9, and T of 4 we have 16. Now it looks like this is a sequence of perfect squares. Now for P of n, this might be a little bit tricky, but let's just suppose that the side lengths of the triangle in pattern 1 are x, y, and z, where x plus y plus z is equal to 7. Now since every small triangle is congruent, we can just plug in the dimensions to the next pattern. So notice that this length right here is just x, as well as this length since these both triangles are congruent. Same thing for here, this is just y and this is just y, this is z and this is just z. So the perimeter for pattern n plus 2 will be 2x plus 2y plus 2z. Notice that we can factor out a 2 and then substitute our value for x plus y plus z to get a perimeter of 2 times 7 or 14. Notice that we can just apply this rule to every single pattern right here. And you'll notice that the perimeters are like multiples of the first pattern. So we have 7, 14, 21, and 28. Notice from right here we can generalize these formulas. So let's see, for T of n, notice that they look like a sequence of perfect squares, and its general formula will be n squared. For P of n, it looks like a sequence of multiples of 7, and its general formula will be 7n. Well, I would say that I would end this video right now, but I want to show you a bonus question. We need to try to prove that the formulas for B are correct. So we want to show that this is always true for every single n. Now before I go into the bonus part, I'm not necessarily saying that this is exactly a proof, because it's more like seeing how this pattern exactly works and how we can generalize how the pattern works to form a formula for T of n and probably for P of n. So just keep that in mind and enjoy this clip. Now I won't do the proof for the formula for P of n because I've just shown like the sketch of it and how it works. So I'm just going to prove the formula for T of n. So let's just see how this pattern exactly works. Notice that if you want to go to the second pattern, you just need to add the first pattern with 1, 2, 3 triangles. Similar thing for if you want to go to the third pattern, you just need to add the second pattern with 1, 2, 3, 4, 5 triangles. And if you want to go to the fourth pattern, you just need to add the third pattern with 1, 2, 3, 4, 5, 6, 7 triangles. And with this, we can try to rewrite our values for T of n. Notice that 1 could just be rewritten as just 1. 4, on the other hand, could be just written as 1 plus 3, where 3 is the number of triangles added to get to the second pattern. Similar thing for T of 3, we can rewrite this as 1 plus 3 plus an additional 5 triangles. And finally for 16, we get this is equal to 1 plus 3 plus 5 plus 7. Notice something similar right here, because notice that these are the sums of odd numbers. And we can see how n relates to the number of odd numbers we're adding. So we have n equals 1 odd numbers being added right here, and we have n equals 2 odd numbers right here. We have n equals 3 odd numbers, and then we have n equals 4 odd numbers. Alright, so now we can rewrite our formula for T of n in terms of adding odd numbers. So we have 1 plus 3 plus 5 plus all the way up to the nth not odd number, which just can be rewritten as 2n minus 1. And you can generalize this formula inductively, and you'll leave with n squared, which completes the proof and also ends this video.